Hey everyone, and welcome to today's Explainer. We are stepping straight into this really vibrant, storybook-style mathematics classroom today to join a secondary math teacher, Mr. Moustafa, and his super eager Omani student, Sami. Today, we're tackling a topic that honestly intimidates a lot of people, but it's actually incredibly elegant once you get the hang of it. We are diving into logarithms from the G12 Advanced Math curriculum, crafted by teacher Moustafa Khedr. Let's just jump right in.
So right off the bat, Sami brings up a frustration that I think pretty much every single one of us has felt at some point in our math journey. He asks his teacher, Mr. Moustafa, how do we handle astronomically large numbers in math without getting entirely confused? And he's got a point, right? Whether you're looking at, the distance between galaxies, the sheer number of cells in the human body, or even just really complex financial calculations, writing out endless strings of zeros is basically a recipe for making a mistake. Sami's looking for a shortcut here. He wants a way to compress these massive, unruly values into something, well, manageable.
And I love this because it perfectly illustrates the role of a fantastic teacher. With genuine enthusiasm, Mr. Moustafa replies, "That's exactly where the magic of logarithms comes in, Sami. Let me show you." He's promising Sami, and really by extension all of us watching this explainer, that logarithms aren't just some abstract, boring hoop you have to jump through for a test. They are actually a highly practical, almost magical mathematical tool that was designed specifically to tame those wild, unwieldy numbers.
Okay, so what is a logarithm? The core definition is actually super simple. Mr. Moustafa explains that a logarithm is, quite simply, the power of 10 that is equal to a specific number. That's really it. When you see the word log on your paper, it's literally just an abbreviation. So if we want to find the log of 100, we just have to ask ourselves, okay, 10 raised to what power is going to give us 100? Well, since 10 squared, or 10 to the power of 2, is 100, the logarithm of 100 is exactly 2. Likewise, the log of 10,000 is 4, simply because 10 to the power of 4 is 10,000. We are literally just extracting the exponent. That's the whole trick.
But you know, Sami is a really sharp student, and he notices this crucial detail in the textbook's Stop and Think section. He asks a brilliant conceptual question. Why is it possible to find a logarithm only for positive numbers, and not for zero or negative numbers? This is such a fantastic mathematical mystery. Like, why does the math suddenly just break down if we try to find the log of -5, or the log of 0? Let's see exactly how Mr. Moustafa builds the answer for him. Alright, so the key here is understanding how our base number 10 actually behaves. Mr. Moustafa maps it out so logically on the whiteboard for Sami. First, remember our definition. A logarithm represents a power of 10. Now, if we take 10 and raise it to a positive power, like 2, obviously we get a positive number, 100. But what happens if the power is negative? Well, if we raise 10 to the power of -3, we don't get a negative number. We actually get a positive decimal, 0.001. No matter what crazy number you put in that exponent spot, whether it's positive, negative, or a fraction, the result of 10 to that power is always going to be greater than 0. Therefore, you literally cannot raise 10 to any power and get 0 or a negative number as your answer. Since the output is always positive, we can only ever take the log of a positive number. Make sense?
To really lock this in your brain, notice how raising 10 to a power and finding the logarithm are perfect inverse operations. Just follow the visual path with me for a second. If you start with a 3 and you raise 10 to that power, so 10 to the power of 3, you arrive at 1,000, right? Now, how do you get back home to that 3? You just take the log of 1,000. It forms this complete, elegant loop. One operation simply undoes the other. Kind of like tying and untying a shoelace.
And seeing this loop sparks a brilliant aha connection for Sami. He looks up and says, wait, if logarithms are just inverse powers of 10, do they follow the laws of indices we already know? Now, this is exactly the kind of active learning we love to see. Sami is connecting his prior knowledge of indices, or exponents if you prefer that term, directly to this brand new, slightly scary concept of logarithms. If they are fundamentally the same exact thing, just functioning in reverse, shouldn't their rules perfectly match up? Oh, Mr. Moustafa is absolutely beaming here because Sami just hit the nail on the head. We can see this beautiful symmetry right here on the board. On the left side, we have our familiar laws of indices. For instance, 10 to the power of a times 10 to the power of b equals 10 to the power of a plus b. We know that one. Now look on the right side. Corresponding exactly to those are the three fundamental laws of logarithms. They aren't just random new rules you have to memorize. They are direct translations of the index laws you already know. Let's actually break them down one by one so you can see exactly how this magic works.
Let's kick things off with Law 1. First, recall that basic rule for indices. To multiply powers with the same base, you just add the indices together. So, applying this logic to logarithms, if we have the log of two numbers being multiplied together, like log of x times y, we can actually split that apart by adding their individual logs. Therefore, log xy elegantly becomes log x plus log y. The multiplication happening inside the log turns into simple addition outside of it. It's really that straightforward.
Moving smoothly right along to Law 2, the pattern completely holds up. Recall your indices again. To divide powers, you subtract the indices. So how does this translate to logs? Well, if you have division going on inside your logarithm, like the log of x divided by y, it splits apart into subtraction. Therefore, log of x over y equals log x minus log y. Just like that, a potentially messy division problem transforms into a super easy subtraction problem.
And finally, let's look at Law 3. Back in the familiar land of indices, to find a power, you multiply the indices. In the world of logarithms, this means if you have an exponent hanging out inside the log, say log of x to the power of k, that exponent doesn't actually have to stay trapped up there. It can drop right down to the front and become a multiplier. Therefore, log of x to the power of k becomes k times log x. Honestly, this is arguably the single most powerful tool in your entire logarithm toolkit, because it allows us to bring those unknown exponents down to ground level where we can actually solve for them. It's a total game changer. Okay, so knowing the rules in theory is great, but applying them? That's where the real learning happens. Mr. Moustafa turns to Sami with an awesome interactive challenge derived straight from the textbook's example 1. Let's put these rules into practice, he says. If we know that log x equals c, how do we write the log of 10 divided by x in terms of c? Now, this is a classic textbook exam-style question, testing whether we can actually manipulate the laws we just learned. Let's see how they do it. Let's actually walk through this solution step by step, exactly how Mr. Moustafa writes it out on the whiteboard for Sami. Step 1. We identify the core operation happening inside the log, which is clearly division, 10 divided by x. Step 2. We immediately apply Law 2, which we know tells us division turns into subtraction. So log 10 over x splits nicely into log 10 minus log x. Step 3. We simplify what we know. Based on our very first definition, 10 to what power equals 10? Well, the power of 1, obviously, so log 10 is simply 1. Now our equation is looking much cleaner, 1 minus log x. Finally, step 4. We substitute the information we were given in the problem. We were told log x equals c, so we literally just replace log x with c, giving us our final, beautifully clean answer, 1 minus c.
Boom, there it is. Looking at this step-by-step breakdown on the board, Sami experiences that wonderful aha moment every student hopes for. He exclaims, wow, so logarithms aren't scary new math, they're just indices in reverse. I can use the rules I already know. And honestly, that beautifully summarizes the core takeaway of our entire explainer today. By tying the intimidating concept of logarithms right back to the familiar everyday rules of exponents, the math becomes totally accessible. The mystery is gone, and it's replaced by pure, elegant logic.
But wait, before Mr. Moustafa lets Sami pack up his backpack, he leaves him, and by extension all of you, with one final provocative thought for the road. He asks, now that you know the laws, explain this. Why does log 10 equal 1, and why does log 1 equal 0? I want you to really look at that question. Apply the core definition of logarithms we just covered today. Think about that base of 10 and exactly what power you need to reach those target numbers. It's the perfect test of true understanding to wrap up our vibrant journey through G12 advanced math. Keep applying these laws, and I promise you, those astronomically large numbers will never, ever confuse you again.